Hi there, welcome. Thank you for joining us here today with Lockheed Martin, a WISA strategic partner, presenting on 5G and cyber threats. My name is Lynn Dome, Women in Cybersecurity Executive Director. We often go by our acronym WICYS, W-I-C-Y-S, as in We Sisters. And that's exactly what we are. We're a cyber sisterhood. We're a 501c3 member-based organization. We have over 5,000 members in 70 countries, and we have 38 professional affiliates in Africa, Australia, Canada, France, India, Pakistan, the UK, and the US. And we have 127 student chapters in Canada, Costa Rica, India, Nigeria, and all throughout the United States. And our mission is to recruit, retain, and advance women in cybersecurity. And we do so by creating opportunities. With our 5,000 members, we have an online member forum where all our members can network and connect. We also have special interest groups in our member forums, such as Latinas in cybersecurity, military spouses, data privacy, cybersecurity law, and much more. We also offer skill development training programs, security training scholarships. We have AWS learning series and many other training programs that are in the pipeline as well. We have newsletters and webinar series, scholarships, grants, and awards, not only for our conference, which is September 8th through the 10th in 2021, this year in Denver, Colorado, and it's also March 16th through the 18th, 2022 in Cleveland, Ohio, but also we issue out scholarship grants and awards to many other conferences and events as well. We have a cyber talent emergency fund designed for students that are within their last 4 semesters of completing their cybersecurity degree. We have speaking and media opportunities because we often want our members to be what others can see and have those opportunities. Our Job Board Plus is the place Lockheed Martin can recruit from our memberships, and all our members can go ahead and upload their profiles, upload their resumes, and get recruited from the Job Board Plus. We have a veterans apprenticeship program. Also, we have an internship program. We participate in market research. We have leadership summits, virtual and in-person career fairs. And we also offer assistance to veterans and military spouses, in addition to having a speakers bureau, and our mentee program is up and going strong. Applications for the 2021 cohort actually just opened up yesterday. So if you're interested in that, please check out our website, weethis.org, and look under initiatives for our mentor-mentee program. Last year, we were super proud to have 707 mentees and 185 mentors in that cohort. We also have our racial equity committee that leads internally within the WISIS organization leadership series on leading with ally inclusion and equity, and what does that look like. And we have many, many more opportunities as well. And we owe all that with a special thanks to our strategic partners, AWS, Bloomberg, Carnegie Mellon Software Engineering Institute, Cisco, Facebook, Google, Lockheed Martin, which brings you the webinar here today, Microsoft, Optum, AbbVie, JP Morgan Chase & Company, LinkedIn, Navy Federal Credit Union, Nike, Sentinel One, Wayfair, Workday, Accenture, American Airlines, Arctic Wolf, Dell Technologies, Envestnet, Flatiron, Fortinet, Haystack Solutions, Here Technologies, the Home Depot, IBM, MITRE, Motorola Solutions, Oak Ridge National Lab, Palo Alto Networks, Salesforce, SANS Institute, SAP, SmoothStack, SpearTip, Starbucks, Target, University of California, San Diego, and Verizon. Whew, we got them all out there. So we thank you, our strategic partners. And so I encourage everyone today, you're here. We got Katie here from Lockheed Martin. We have an incredible webinar and a presentation for you ahead. So we'd like you to ask a lot of questions. At the bottom of your window, you see that there's the chat function there. Please put your questions there. And Katie, at the end of her presentation, will be sure to get to those. And if you haven't done so already, subscribe to our newsletter. That is the quickest, bestest, fastest way to keep up to date with all things WISIS. We roll out these training programs, opportunities, scholarships, you name it, they're rolling out at a rapid rate. And so paying attention to our newsletters and emails that come your way are the greatest way to stay connected to the community. So without further ado, I'm going to hand it over to Katie from Lockheed Martin. Katie, take it away.
All right, thanks, Lynn. So good afternoon, everyone, or I guess it's good morning if you're on the West Coast. I'm Katie Grzywacz. I work for Lockheed Martin Space as a cyber architect, and I am the chief cyber architect of our space centers of excellence. I've been doing some research on 5G. It's an interesting technology. So I guess it was last year, right, I heard a call for 5G security expertise, and I thought, hey, that sounds pretty interesting. I wonder who's working on that, and then the answer turned out to be me. So I wanted to take some time to share with you some things I learned about 5G and cyber. I'm going to start by talking about what 5G is. If you don't know anything about 5G, that's totally fine. I'm going to start with the basics, talk about what the concepts are that make up 5G, and then we're going to transition over to talking about cyber threats. So I'll give you a high level of concept of all of the threats that can come into play when we talk about national security. All right, so what is 5G, right? When the topic of cellular technology comes up, we inevitably start hearing about Gs. So the G stands for generation. And in the 80s, we had the creation of the first wireless telecommunication standard. So that's our 1G. 1G was voice-only analog, and it was not very fast. People use these ginormous cell phones like the Motorola Dynatac you see in the photo on the left-hand side of the screen. This was also the phone that Zach Morris used on Saved by the Bell, for anybody who watched that. And then there were other popular phones that started being used as we moved into the 90s. So the second picture may be a little hard to see because it's kind of cropped, but that's what we would call like a bag phone or a car phone. It had this receiver with a cord that attached this black bag, and then you would plug the bag into the cigarette lighter on your car for power, and that was a car phone. So my mom actually had one of those when I was a little kid, and it was really fun to use. But anyway, in the early 90s, we had 2G come about. So 2G brought us digital voice and higher speeds. And then we also had the introduction of features like SMS and MMS. We weren't really using those features like we do today, but they existed back then. And then later in the 90s, we had 3G, which introduced the concept of mobile data. So we had things like mobile internet, supposedly video calling, which again, wasn't really used like we're using it today, right? There was no FaceTime or Skype yet. But the important thing was that the speed was much faster than in the previous generations. So now you have the ability and the potential to do those things. We also got better phones. So rather than that like candy bar Nokia phone style that was really popular, we started having phones with color display screens. Things like Blackberries or Sidekicks that would display an entire text message on your screen without scrolling, or the Motorola Razr was also really popular. And then as we moved into the 2000s, smartphones were invented. So we finally had phones that acted more like computers. They had, really nice screens, they had more processing power, and there were a lot of apps that really started harnessing the power of mobile internet. Cellular technology getting better, so we have much faster data. I have a note here that it was faster, or 500 times faster than 3G, which was a huge deal. So we started doing more things that relied on that speed. We had things like video conferencing, or we could stream videos from like YouTube or Netflix. So it was just overall a much better user experience, and we could do stuff quickly. Now we are in the beginnings of 5G. So 5G is able to provide a much faster data service. The peak is supposedly like 10 to 20 gigabits per second, although in practical use, average speed would be a lot lower, probably in the hundreds of megabits per second or more close to 100. So speed's not the only improvement. We also have more capacity to connect more devices. And then one of the huge improvements that 5G breaks ultra low latency. So latency, if you don't remember what that is kind of like a time delay. So let's say you're a user sending a request to something like a server, and then the server responds to your request. Latency would be how long it takes for that response to come all the way back to you. So with 5G, rather than it taking like maybe 50 milliseconds to get your response in 4G, in 5G, you're looking at potentially a much lower time. So maybe in like the 1 to 3 millisecond range at a top performance, which is pretty fast. So you might be wondering, okay, how were they able to improve so many aspects of service with 5G? And the answer is that 5G does that by offering 3 different services, and they utilize the different bands you see on the screen. So in 5G, our 3 services are enhanced mobile broadband, ultra reliable low latency communications, and massive machine type communications. So EMBB, which is enhanced mobile broadband, is probably what you're thinking of when you think 5G. It gives you a really stable connection with a very high peak data rate. So of the 3 service options, it's the fastest. It also operates on the highest band. So when you have a higher frequency, that typically means less coverage. So in order to get those high speeds, you need to have more 5G transmitters. So if you live in an urban area, you're more likely to be in an area where you have the density of those transmitters to support EMBB service. If you're in a more rural area, so let's kind of go to extremes. You live on an isolated ranch in Wyoming that covers a few square miles, you're probably not going to have the coverage there. I think EMBB supports maybe a mile of coverage, assuming there's no interference, so no buildings or anything in the way. So that's EMBB. The next service is URLLC, which is ultra reliable low latency communications. That's what's operating on the midband. So it's not as fast, but in exchange for speed, you have better coverage. So it covers, I think, a few miles, and you don't need as many transmitters. URLLC is a huge deal because it provides very low latency and very high reliability. So that is not something that we had before. So now you're going to be able to use 5G service to support things that are time sensitive. So that includes things like mission critical apps or anything where a decision needs to be made very quickly. Potentially, if you think about how we might use it one day, it could support things like self-driving cars or even just safety features in cars. Or things like virtual reality, all sorts of use cases where you truly do want a response in that like 1 millisecond range. So think about a use case where you're playing some sort of virtual reality video game and you have some sort of headset that corresponds to how you move around in real life. So if you move around and it takes 50 milliseconds for the video feed to catch up to your movement, right, it's going to be pretty laggy, maybe even unusable. That's a pretty innocuous use case. If you play a video game, the counts is low, but if you think about other potential uses like autonomous driving or like remote robotic surgery, flying drones, etc., it's a huge deal, right? People could die or become injured. You could crash your drone or your car or damage property. So you definitely want guaranteed ultra low latency in those cases. So it's pretty exciting. And then the last service we have is called massive machine type communications. So that's using the lowest band, and in exchange for that, you get better coverage. So you need fewer towers. If you're in an area where coverage is poor, MMTC could probably improve your terrestrial coverage, but then with that improved coverage comes lower speed. So there's always a trade-off. MMTC is designed to target IoT devices. So I'm sure we all know what IoT devices are. But if you forget, it stands for Internet of Things. So you have like a paradigm where you have all sorts of devices connected, usually small devices, things with sensors, wearable devices, or things that communicate infrequently. So all of those types of things might be best supported by MMTC. And you may have heard about how MMTC supports devices that are battery operated because it can enable them to use less power. So you have technologies like LTE-M or narrowband IoT that come into play when we talk about MMTC, although we don't have time to discuss them in the time we have today. But basically, what you need to know is that you can have a simple device, so maybe something like a smart power meter or some other sensor that uses MMTC, and it communicates in a way that's designed to be efficient and use less power. So the actual calls home are more efficient, doesn't require as much power, and then the devices themselves are also not intended to be chatty. So maybe you have like a smart meter that reports once a week, or I guess it could report once a month, or on demand, so very infrequent usage. All right, so we talked a lot about use cases and how they're enabled by the different 5G services. It's not just a matter of having faster speeds for our smartphones, and we're going to see other use cases and new types of devices using 5G connectivity that goes beyond what we typically think about with our smartphones using cell phone service, and that's kind of it. So I work for Lockheed, so I'm naturally interested in what the Department of Defense has to say. So I thought this was an interesting snippet. About a year ago, the DoD had put out a 5G strategy. It's published on the internet for anyone who's curious to read it. And I thought it was interesting to see their take on how 5G could cause a big change. So in the blue box, there's a quote, and it says, let's see, "Ubiquitous high-speed connectivity will also transform the way militaries operate. Tomorrow's warfighters will use local and expeditionary 5G networks to move massive amounts of data to connect distant sensors and weapons into a dense, resilient battlefield network. This data-rich environment will fuel powerful algorithms that will allow commanders to better understand, shape, and adapt to complex and contested physical and information environments." And then it goes on from there, talking about how low latency and using like 5G to operate with speed, precision, and efficiency. So you can kind of see many types of use cases that would enable total paradigm shifts for a lot of things. This is just one example, but we're going to see a lot coming in the future years. All right, so we've talked about how 5G services enable use cases. That's a pretty important thing to understand if you're concerned about securing devices, right? It's hard to protect or attack a system if you don't understand the ConOps or how these devices should work. There's a few other basic concepts I'm going to touch on that are also important. So this is going to be somewhat high level, but if we're going to talk about attacking 5G systems or threats to 5G, then it might involve attacking some of these things, or it might rely on some of these concepts. So just bear with me for a couple slides. All right, so 5G networks provide so backhaul network is when you get stuff from the radio towers that serve the signals to your phone back to the 5G core. And the core is the core network back at your telecom. 5G networks were designed to be very configurable, and then there's a few concepts that support this. So you have software-defined networking, network functions virtualization, and service-based architecture. So software-defined networking involves dynamic network management. In 5G, you have what's known as the control plane and the user plane, sometimes called data plane. So the control plane is doing things like routing the traffic, and then the data plane or the user plane is where the user is. So those are separated. And then you can use things like software-defined networking to maintain that separation, and you can do things like reprogram the data plane as needed based on utilization and other things. So it's a very flexible network. You also have network function virtualization, which is when you use like a network, a virtual network appliance rather than having dedicated hardware. So that's used with software-defined networking, and it offers flexibility. So if you have a dynamic network that is reprogramming itself or readjusting itself, it lets you spin up more resources if they're virtual. So nobody has to, go to the data center and plug stuff in. It's all able to be automated. We should probably also mention network slicing. So we have our network function virtualization and software-defined networking, which are used to enable this concept network slicing. And that's when the carriers are going to divide parts of the network for specific customer groups. So you might have like certain customers that get grouped together on a slice, and then the slice offers different prioritization or quality of service. So you might have like one user group that pays for higher speeds and their service agreement says they can't drop below minimum speed, or you have like another subset of users who, like per their agreement, are totally fine dropping below that speed that the other group can't. Or maybe you have types of users. So you could have users like first responders who might have a dedicated network slice that is more highly prioritized, because in an emergency, right, you want to make sure that the EMS can communicate versus, someone who's bored and is trying to stream a video on Netflix. And then we have service-based architecture, which is a very popular concept, widely used. You have like reusable software components with interfaces that expose functions they offer. So you can think of things like web services would be an example. And then we also have this thing called the MEC. So MEC is pretty important in 5G, and it stands for multi-access edge computing. So the MEC exists for latency reasons. If you think about how you might access an application today from your phone, right? You're probably on your phone, you're connecting to the radio access network, which is what's serving your phone the signal. That will then send some traffic via the core network, which then might send it on to a data network like the internet. And then on the internet, interact with like a cloud service. It does some processing for you. And then everything gets sent back through all those hops to your phone. Right, so you could have a lot of hops, which could take time to navigate, and it could cause a lower latency. So with the MEC, we have a concept where we're taking some of those like cloud services that might have been on the internet somewhere, and instead of leaving it on the internet, we're moving them into the RAN, which is the radio access network. So now your latency is much lower because you don't have to traverse as far. You've moved like all of the necessary computing resources much closer to the user, right? If they're in the radio access network, that's like one hop maybe. So let's say you have a service that supports something mission critical like autonomous driving. That is an example of thing that would be MEC, because you need that ultra low latency. So that's a huge reason for the MEC. It also has a few other benefits too, like data localization. So, when you're on the tower, right, that users are probably within a certain area that's proximate to that tower. So there might be specific rules you would apply that pertain to local laws. Or maybe you would try to restrict data from living places it doesn't need to improve privacy. So you're like consolidating data on the RAN instead of pushing it to some centralized network somewhere. So that's DMEC. It's important for 5G. And then we have more concepts too. So you see this UE acronym. UE stands for equipment, something like phone or any other device that uses 5G, like an IoT device or anything that has like a 5G modem on it. So your phone or your UE takes data, it turns it into radio waves. They send it to the radio network, and then to receive data, the opposite happens. So you get radio waves from the RAN, and then your phone translates that into data, which then you can use. We also have the RAN, which stands for Radio Access Network. That's basically the towers that provide the signals to your phone, and it connects them to the core network. So the components there are things like antenna, radios, baseband units. You have O-RAN and C-RAN. O-RAN specific bands. C-RAN is like a cloud computing architecture for radio access networks. And then you have these things called G-Node Bs and E-Node Bs. So a G-Node B is basically what we call a 5G base station. And it has a few components, CUs and DUs that make it up. We also have E-Node Bs, which are a version of a 4G LTE base station. So G-Node B is 5G, E-Node B is 4G. And then finally, our last acronym is CN, which stands for the 5G core network. This is like the heart of 5G, where you manage everything that comes in from the RAN. So you might give access to the UE, route some traffic, and then the core network has a bunch of services in it. All right, so network. The 5G core uses that service-based architecture that we talked about. So you can see on the screen, there are a whole bunch of different network functions, and they do lots of different things. So they enable access to that network and mobility management. They do things like session management, manage network slicing, there's authentication services, policy, and so on. If you look at the bottom diagram, it shows the UE connecting via the RAN to the AMF, which is the access and mobility management function. So the AMF gets access to the network, and via that service, lots of other services are called. We also have the UPF, which is the user plane function, which connects the network like the internet. So this is all from the 3GPP spec, and 3GPP is a standards body. So if you're curious about learning more, you can go out to 3gpp.org and look at some of the documentation. So 5G starts in their release 15. All right, so there are a couple different architectures we should talk about. So in 5G, we have the concept of non-standalone versus standalone architecture. And as telecom companies are transitioning to 5G, many of them are doing it, upgrading their current system, right? Building an entirely new system is somewhat cost prohibitive, and also seems like it would be very complicated. So you would probably logically just want to upgrade your existing system to support 5G. So that's where we have these NSA, which stands for non-standalone architecture here, that are the intermediary to the standalone architecture, which is what you see on the right-hand side of the screen. So right on the NSA, you have, you can see that you have G-Node Bs and E-Node Bs. So you're getting both 5G and 4G services, and probably other previous generations as well. And then it might still be using what's known as the evolved packet core, which is the 4G LTE core rather than 5G. It's who is running the network and how they are transitioning. And then the important thing about non-standalone is that you have those different services available. So you have 5G, and if you have a phone that supports 5G service, you can use it. But then you could also be downgraded to previous generations. So maybe you might want to use 5G, but you're actually getting 4G service or even previous Gs. So that's an important concept to understand. And then on the right-hand side, you can see this is a very straightforward network. You have your G node Bs, no E node Bs, so no 4G. This is all pure 5G, and you can see some of the functions from the core. All right, so that was my quick 5G background. Now we're going to transition to talk on. When you think about cybersecurity, there's a lot of angles to take. So I'm going to try to talk about them related to national security, because that's pretty generic. We've probably all sort of thought about this kind of topic. And I'm actually going to talk through a paper called Potential Threat Vectors to 5G Infrastructure. So this was a paper that was written via a partnership called the Enduring Security Framework. So it involved government agencies like the NSA, the National Security Agency, not the non-standalone, as well as private companies like Lockheed. So I participated in this panel along with one of my coworkers from Lockheed, Mark Hoffman, plus various other groups, which is how I came to choose this as the focus for a mini discussion. All right, so overview of threat vectors. When you think about national infrastructure, you can kind of divide threats into a few categories. So the first category is policy and standards. The second is supply chain. And the third is architecture. So if we think about open standards, you might want to think about how those standards come to be. And what they include. So maybe there are parties who are contributing to the development of standards that have a goal in mind, right? Maybe they have a technology that they've patented and they want to influence standards to use that technology to get, some kind of competitive advantage. Standards also to include things like security controls, which is great, but sometimes those controls are optional rather than part of the de facto standard. So I'm sure working in security, a lot of us have seen things like optional security controls where we could have secured things, but it got overlooked. Or maybe even if we think about concepts like cyber hygiene, people install software or systems all the time with default options. So maybe, you leave like default passwords on things like your router interface, or even if you look at things like BMC devices, management devices, you forget to set your encryption cipher. So you end up with a null cipher, which means it's not encrypted. So all of those things can negatively impact security posture. Then you have things like supply chain, which with 5G, like anything else, there's always a risk that you could obtain software or hardware that's maliciously tampered with via the supply chain. So maybe someone adds a rootkit or modifies software before it gets sent to you, and then you unwittingly install malware on your system. We've seen tons and tons of supply chain attacks. If we think about big ones in the news, I think SolarWinds comes to mind, right? So SolarWinds was like a network management software. It was hacked and then sent to many customers. So you installed updates that had embedded malware. Right, potential huge impact. You can also have counterfeiting issues with supply chain. So maybe, you go buy equipment from, some store online, and you get a really good price on it, but it's counterfeited. So it's to look okay, but it's not truly genuine equipment. It doesn't effectively implement all the standards in the way that it should, which would then impact things like performance and reliability. And those are pretty important if you think of something like 5G or your cellular communications network as part of your national infrastructure. And then the biggest category is our technical side, systems architecture. So there's lots of potential issues here. I'm going to skip ahead a couple slides and talk to some of the specific threat vectors that relate to architecture. All right, so one threat vector that pertains to 5G architecture is software integration. So you could have a threat that a malicious actor with unauthorized access to software or network components could do something like manipulate configurations of systems with the goal of reducing controls. Maybe they want to introduce malware, or maybe they even just want to identify weak areas which they could exploit. So this is something that is pretty common with most IT networks, right? There's always a threat that software could be compromised and allow for adversary presence on systems. And then our next vector is network security, which again is something we commonly see on IT networks. There's always a risk that a malicious party could try to compromise the network layer and utilize those kinds of exploits to gain unauthorized access to the network. I mean, think about, let's see, common vulnerability or popular vulnerabilities that have been in news like 9/11 on the network stack. And then exploiting this kind of thing might enable disruption, let's see, data disclosure, data manipulation, or destruction of critical data. And then one of the big threat vectors to 5G networks involves legacy infrastructure. So we talked about how 5G networks are not necessarily pure 5G, right? We have non-standalone networks which may support 4G or maybe even 3G or 2G or 1G maybe. So if you're a user connecting to a network, your signal could potentially be downgraded to a previous generation, which would mean that weaknesses with those protocols or services might not exist in 5G, but they do in the generation that you're using. So trying to think of some examples. Some of you might have heard of Stingray attacks, which is Stingray is a device that is also known as an IMSI catcher. And what they do is they simulate a cell phone tower with a goal of trying to trick like a phone or your UE that's on the ground into connecting to it. So it usually does that by mimicking a base station, and it appears like it's really strong, so your phone naturally wants to connect to the strongest base station in the area. So that's like a man-in-the-middle attack that can happen. And then, if you've read the 5G specs, you would know that 5G doesn't even use IMSI, which unfortunately didn't get into all the security improvements in 5G. But you would have IMSI, which isn't used in 5G, but maybe it would be used in 4G. So if you look at an example like the scenario that's in the blue box on the right-hand side of the screen, you have a situation where there's a threat actor and they do something similar to set up a small cell to allow for 4G network spoofing. So 4G has associations with legacy protocols too, like SS7, which is a signaling protocol that had a number of vulnerabilities associated with it. So you could have an attacker try to exploit some of those vulnerabilities. Maybe they do something like denial of service, and they take advantage of some vulnerability that prevents network operators from being able to distinguish between fake and legitimate traffic, so they can't tell what's real or what's fake, so they get overwhelmed and can't block fake traffic. Maybe even something worse. The example we have in the paper is that it could enable an exploit that would then facilitate access to some sort of component that resides in the network and allow for further penetration, maybe ultimately resulting in consequences like sensitive data disclosure. There's more threats too. So that includes threats to things like network slicing and the MAC. We talked a little bit about how network slices can be used to segment user types, and they can provide different qualities of service, but there aren't really guidelines on network slice security, and if you are not managing your network well, there's a risk that there could be some sort of maybe an access violation or a trust violation between the slices. Maybe there's impact to the quality of service of the users that are on the different slices. Or maybe if we even try to imagine a worst case scenario, we could have prioritized users like emergency responders trying to use the network to coordinate response actions, and they're not able to access the system and effectively help save people's lives. We also have threats that are associated with the MAC. So the MAC is when we're taking computing power and putting it closer to the user in the RAM, if you remember. And then having stuff in the RAM is going to open up a new attack surface, because now we can think about having malware in the MAC or different vulnerabilities in the MAC that an adversary could try to exploit. So in the scenario in the blue box, we're talking about a threat actor who gains persistent access to the MAC. And then they use that access to interfere with latency and deny service. So maybe you have a threat actor in there stealing sensitive data, modifying data, denying access. And then if they have a presence within the MAC, maybe they've compromised an application hosted there, for example, they could try to use that access to attack other stuff in the RAN, right? There's all sorts of sensitive stuff in there, right? You have your G-Node B, which has like a scheduler to grant access to UE. Maybe if they have the right access, they could try to clone UE devices. So lots of potential attack surface there. And then we also have even more threats. So one threat is related to this concept called spectrum sharing. Spectrum sharing is when you have one user who might kind of like own a dedicated spectrum, who would then share it with other users. So maybe I own the spectrum, I'm not fully utilizing it, and I'm going to allow other people to utilize it too. So you may have conflicting parties that are competing for access to that space. Maybe somebody wants to get access to whatever those parties are hosting or accessing via that spectrum. Maybe there are people that are trying to leverage whatever supporting infrastructure it uses to gain an advantage, right? Because if we think about the concept of spectrum sharing, there has to be some sort of infrastructure that would support like usage, or how do you know when you can allocate certain space? So there's all kinds of considerations. Maybe even information disclosure if you try to hack that underlying infrastructure. So one example of spectrum sharing is called CBRS, which is the Citizens Broadband Radio Service. So if you're curious about what spectrum sharing is, I think there's a lot of information published about that online. So you can go kind of look that up and get familiarity with that concept. That's not going to necessarily apply to everything. And then you also have a threat vector that pertains to software-defined networking. So software-defined networking has a lot of advantages when it comes to network management, right? You can kind of adapt to whatever the needs are at the moment. But then conversely, right, there's potential for like malicious code to be embedded, or maybe for attacks to target that SDN framework and maybe even interfere with their ability to provide appropriate resources or bandwidth. So yet another threat vector. All right, so that kind of sums up a quick overview of our threat vectors. But if you would like to see a more in-depth overview of the threats, definitely go out to cisa.gov. You can download that threat paper. I think it's also hosted on other government sites as well. And it's called Potential Threat Vectors to 5G Infrastructure. So fun reading. I've really learned a lot about 5G over the past year or so. So I wanted to share some things that I thought were helpful to me. The first step, if you're learning about 5G, is definitely 3GPP, which is the standards body releasing all of the 5G specs. Release 15 was kind of like the 5G. 16 had more details, and then 17 hasn't been released yet, but it's in progress, and you can look forward to that being released in the future. I also have a link to the CISA's 5G page. And then I found some other papers useful too, as well. So 5G Americas has a nice security paper. There is ENISA, which is an EU body, had a nice overview of like security and 5G specs. So it might be a little easier to read than the 3GPP spec. I didn't have any time to include discussion of security features, so definitely go out and read it if you're interested. And then let's see, there's also the Palindrome Tech Report, which is another like threat and risk paper that I thought was interesting reading. And then if you're interested in a book, I didn't include this on the slide, but I have taken a class by a couple professors who work at Virginia Tech, Dr. Richard Pathy and Dr. Reed. And I know they've published a book called 5G Cellular Communications, Journey and Destination. So I haven't read the book, but I really enjoyed the class that they taught. So it might be a nice resource to learn about the inner workings of 5G as well. All right. So let's turn it over to questions. So I'm gonna turn my camera back on so you can see my smiling face. Let's see. All right, so hey everyone, I already see some questions in the queue, which is great. If you do have questions, please go ahead and submit them. I'm gonna read through some of the questions and we can talk about them. So the first question we have is about 5G services. So the question says, imaging seems like it would really benefit from your LLC, like a medical case. Yeah, I would definitely agree with that. I think there's all sorts of medical use cases, especially if you're in maybe a more rural area that might be able to take advantage of services that are offered elsewhere. One of the really common medical use cases I've seen talked about is robotic surgery. So pretty dramatic to be doing remote surgery, but maybe it's the way of the future, who knows? The next question, does EMBB have higher latency? So my experience in my rural area with a 5G service was about highly. So yeah, so EMBB is not the one that's designed for ultra low latency. That's the URLLC service. So you could definitely experience higher latency with EMBB, but you do get faster speed. And then looks like there's one more question. What is your description of the term defense forward within 5G? I'm not sure. Actually, I don't think I've ever heard that term before. So I will have to say that I don't know. And then let's see, this will be interesting to figure out how to emulate for testing in virtual cloud environments. Is the presentation going to be available by chance? I believe WeSys does make the slides available to download. So maybe we can look for that after the presentation. Oh, and Lynn says, the organizer, says that you can also email info@wesys.org to get a copy of the slides. So again, if you're interested in the slides, you can email info@wesys.org. All right, so thank you so much, everyone. I hope you were able to learn something about 5G from the presentation, and I really enjoyed presenting. Thank you.